Hello, everybody. I'm starting a new topic here. This is chapter 12, I believe, which relates to statically indeterminate beams. And statically indeterminate, if you guys recall from axially loaded members, of course, we were doing a different type of problems there. But statically indeterminate basically means that you have too many unknowns and not enough equations to solve the problem. So for example, here, look at this beam that I have as an example to describe the method. Here, you see that we have a cantilever beam, right? This cantilever beam, and you have a load right in the middle, a concentrated load, and then you have this roller here at B. So if we draw a free body diagram for this guy, we have a reaction here, vertical reaction here, no x component of reaction, a moment reaction, and a reaction here. So that's 1, 2, 3 unknowns, m sub a, the moment reaction, ay, and by. And there are only two equations. Remember, I cannot use the equation in the x direction because there is basically nothing in the x direction. So that leaves us sum of the forces in y equals 0 and sum of the moment about any point equal to 0. Two equations, but three unknowns. That makes it statically indeterminate. Okay, so what I want to show you, you could actually solve statically indeterminate problems here in this chapter using all the methods that I mentioned in the other videos, like integration method, superposition method, energy method, moment area method. But remember, we want to concentrate specifically in this chapter only on superposition. So this is going to be a short chapter, guys. I'm going to just make two short videos on this. One example here and one example coming shortly after this video related to simply supported beams. Okay, so what's the remedy? How do we get around this? How could we solve for all these unknowns? A sub y, m sub a, and by. Of course, our concentration is going to be on b sub y. Once we find b sub y, then we have two equations, two equilibrium equations. We can solve the problem. Okay, so this is how we're going to do it. So basically, forget about, the reactions here, m sub a and a sub y. Put this cantilever back and just expose this reaction b sub y here from the roller. Then look at this beam. How would this beam deflect? This beam would deflect like this, right? So we know deflection has to be 0 because we have a support there. Now, we're going to now use superposition, basically divide this beam into two beams, one with the concentrated load in the middle and one with just the this reaction, which just got erased somehow, b sub y in this direction. Okay, I pause for a second. So the deflection due to b sub y is going to be upward, and here I call it b y sub b2. Okay, so now I have this table here on the side for you. So due to the load in the middle, we're going to go and use this. And look, the maximum deflection which happens right here is given as 5 PL cube over 48 EI. Now you have to watch for the sign. So this is a downward deflection. So this is the deflection here, minus 5 PL cube over 48 EI. And then due to this unknown b sub y, we're going to use this. And obviously this is an upward deflection, so it would be positive. And that's PL cube over 3EI, but instead of P here, put BY, and would be BYL cube over 3EI. So obviously EI is going to get cancelled, and then you can just simplify this and find BY. So you see how easy it was to figure out the reaction. So once you have the reaction at BY, then look at this free body diagram here, and then you can go ahead and take moment, for example, about A, say it equals 0, find, say, and also sum of the forces in y equals 0. So for example, this one is clear that AY plus BY must be equal to P. So if BY is 5/16 P, AY must be what? Must be 11/16 P. And then, so you have your AY. And then, of course, you can take moment about A and find M sub A. Okay, so hopefully this made sense to you. And I'll come back soon with another example to wrap this up so we can move on to more important topics and lectures. Thank you for watching and listening.